cancels out. So this is how we determine the number of moles of carbon dioxide in water. Why do we need to determine the number of moles? Because if you know the number of moles of carbon dioxide, you would know the number of moles of carbon in carbon dioxide, because each mole of carbon dioxide has 1 mole of carbon in there, CO2, C1O2. Okay? And if you know the number of moles of water, you would be able to determine the number of moles of hydrogen in there, because each mole of water has 2 moles of hydrogen in there. Multiplying the number of moles of water by 2, you get the number of moles of hydrogen. All we're trying to do here is to determine the molar ratio between carbon and hydrogen. If we can determine the carbon and hydrogen, number of moles of carbon and hydrogen there, we get the ratio between the two. The other task would be determine the number of moles of oxygen. Okay, so we'll show you an example there. Now, if you do this calculation, this is the answer you're supposed to get. And if you divide 1.5 by 44.01, you get 0.03408 mole of carbon dioxide. Okay, and you get 0.02248 mole of water. Okay, so that's the first step. Second step there, we can determine the number of moles of carbon and hydrogen in the original compound. Okay, so if each mole of carbon dioxide has 1 mole of carbon in there, then if you have 0.03408 mole of carbon dioxide, you have 0.03408 mole of carbon, 1-to-1 ratio. The number of moles of hydrogen is twice as much as the number of moles of water, 0.02248 times 2, okay, that will give you 0.04496 moles of hydrogen. Okay. Now, if we stop here, we will be able to determine, dividing this number by this number, because this is the smaller number between the two. Okay? In this case, if you divide the bigger number by the smaller number, you will be able to determine the molar ratio between hydrogen and carbon. But we have another component there. We have an oxygen in this compound here. So we have to go one step further, and we have to figure out the number of moles of oxygen. Now, the thing here is that if you try to determine the number of moles of oxygen there, you cannot determine the mass of the oxygen based on the mass of carbon dioxide or mass of water. Because in carbon dioxide and water, oxygen comes from 2 different sources. One is the original compound. The other is the oxygen gas you supply in the burning process. So you can't simply add these two numbers together, okay, and then based on the mass of the oxygen here, the mass of oxygen here, to determine the mass of oxygen from the original sample there, because those oxygens, these oxygens come from 2 different sources there. Okay. Now the thing here is that if you have 1 gram of the sample, and we also have 0.4093 gram of carbon, where do you get this number? Well, we know the number of moles of carbon we have in the sample. Multiply the conversion factor, which is each mole is equivalent to 12.011 gram. Now we know how many grams of carbon we have there, and that the product of these two numbers there gives you 0.4093 grams of carbon. So we know for this many moles of carbon that we determined from the previous 2 steps there, that's equivalent to this many grams. We do the same thing as for hydrogen there. Now, we know that we have 0.04496 mole of hydrogen in the original compound. Each mole of hydrogen is 1.0079 grams. This number comes from the periodic table. Okay, so we get the moles of a hydrogen there. Total mass of the sample, mass of carbon, mass of hydrogen. The difference between the total mass and the mass of carbon and hydrogen would be the mass of oxygen here. So mass of the oxygen equals 1 gram, that's the total mass, minus the sum of the carbon and hydrogen in the original sample there. I will give you 0.545 gram of oxygen. So this is the way that we can determine the mass of oxygen. Now once you have the mass of oxygen, you can convert it into moles. Okay. When you convert it into moles there, 0.545 gram, dimensional analysis, multiply the conversion factor, each mole 15 grams or 16 grams. Okay, gram and gram cancels out. I will give you the number of moles there. Okay, so 0.03406 moles. So this is how we determine the number of moles of carbon, hydrogen, and oxygen in this given sample based on the information given in this particular process. Now we're ready to determine the empirical formula for this compound there. this is how we come up with the number of moles there, okay? Hydrogen, carbon, and oxygen. Now, looking at all those three numbers there, the smallest number is 0.03408, 08 and 1. These two numbers are pretty close to one another. So this number is small r, okay? So we're going to divide all these three numbers by the smallest number, okay? The smallest number divided by itself is 1, and this divided by the smallest number, roughly about 1. And then this number divided by 0.03408. This is, we can come up with what we call a trial formula. This is what we got. Well, we don't like fractions. We don't like decimals. Okay, so this is the number there. And then if you divide everything by the smallest number there, this is what we got. Okay, carbon 1, hydrogen 1.32, oxygen. We still don't like this formula. Now, when you look at the chemical formula in chemical literature there, you don't normally see this kind of numbers. We need the simplest whole number ratio. How do you get the simplest whole number ratio? Well, that's a question. It depends on how you want to manipulate the numbers there. Okay. Now, if you know if you know your numbers well, there are things that you can do to convert that ratio 1 to 1.32 to 1 into a whole number ratio. Now, assuming you know your number well, 1.32, well, 0.32 is like somewhere around 1/3. So that's 1/3. So 1.32 is roughly about 1/3. And 1/3 is 4/3. Okay? So that's one approach. Now, if 1.32 is equivalent to 4 to 3, then our formula would be carbon, hydrogen 4/3, oxygen. Now, we don't like fractions. We multiply everything by the denominator, 3. That will give you carbon 3, hydrogen 4, oxygen 3. That is, you know your number well. Now, if you end up with, say, 1.67, you know that's equivalent to 1/2, and you need to be able to manipulate the number, converting the decimal into fraction there, and you need to know your numbers well in order to do this. Okay, so if it's 1/2, that's 5/3, and then you plug 5/3 in here, multiply everything by 3, come up with the input formula. So the numbers there, you got to know your numbers well. This is the approach that you can use. Okay, so in our case, when we say 1.32, roughly that's about 1/3. 1/3 is 4/3. You plug in 4/3 in here. If you don't like the denominator, you multiply everything by the denominator. This is the formula. There's another approach. Okay. Now, if you come up with this number here, okay, if you come up with this formula there, and we have carbon 1, hydrogen 1.32, oxygen 1. And we don't want to play with the numbers there. We just do trial and error thing. Okay? This is 1 to 1.32 to 1. Now, we don't like this number. So let's multiply everything by 2. Everything we mean the subscript here. It's 1, 1, 1.32. So if you multiply everything by 2, you get carbon 2, hydrogen 2.64, oxygen 2. Still, 2.64. We don't like this number. Okay, well, it doesn't work. Hasn't worked.